So picture this. You have this highly advanced $1 million piece of robotics.
Oh, yeah, like one of those viral videos.
Exactly. It's got hydraulic legs, stereoscopic cameras, gyroscopic balance, the works. And it is just walking blindly straight into a brick wall over and over and over again.
It's totally wrecking itself.
Right. Scraping expensive metal against drywall.
Yeah.
And, why is it doing that? Because nobody taught the software how to ask a very simple question. Like, is there a wall in front of me?
It has no logic.
Exactly. It lacks logic entirely. It's a program without conditions.
Yeah.
So today, we are giving that robot a brain. Welcome to this deep dive. If you're listening right now and you want to understand how the apps on your phone actually make decisions, well, we are unpacking the absolute foundation of how software thinks. Python conditions.
Yeah, because software without conditions is basically just a conveyor belt.
A conveyor belt.
Yeah, I mean, it turns on, it runs straight, and it crashes. But when we introduce conditions, we are introducing choices. And when you strip away all the complex jargon, a condition is just a structured question built entirely on two concepts, true and false.
Just true and false.
That's it. If a programmer can understand how to ask a question that results in a true or false answer, they can build like almost any logic system in the world.
Okay, so before we teach our program to make a decision, we have to figure out how to even ask that question. You mentioned true and false. In programming, those have a specific name, right?
Yeah.
But for someone brand new to this, why do we need a special category for just two words?
So they're called Booleans, named after George Boole, this 19th century mathematician who essentially invented this kind of algebraic logic. A condition is simply a test that always, without fail, gives a Boolean answer, true or false.
No gray area.
Right. There is no maybe in programming. There's no, I think so. If a program asks, is 5 greater than 2, Python evaluates that logic, and underneath it all, the computer literally replaces that entire mathematical question in its memory with the single Boolean value.
True. Okay, I'm tracking with greater than, less than, greater than, or equal to. Those are basic math operators. But wait, let's say I'm building a simple app to check if someone is old enough to vote. If I type age equals 18 with a standard equals sign, the program completely breaks.
Oh, yeah.
We've been using that symbol since first grade math. Why doesn't the computer understand it?
Well, what's fascinating here is that this is universally the biggest trap for anyone writing their first lines of code. In Python, a single equals sign and a double equals sign do completely different jobs.
Completely different.
Completely. A single equals sign is not a question, it is an assignment. Think of it as a name tag or like a label on a cardboard box. When you type age equals 18, you are giving the computer a direct order.
Like a command.
Exactly. You are saying, take the number 18, create a box in your memory, label that box age, and shove the 18 inside. You're stating a fact, not asking a question.
So I'm basically aggressively renaming things instead of testing them.
Precisely the opposite of checking a condition. To actually ask a question, we must use the double equal sign, two equal signs side by side.
Gotcha.
Writing age equals 18 means, hey, Python, go find the box labeled age, open it up, and tell me, is the number inside exactly the same as 18? Python will look, compare the two, and hand back that Boolean, true or false.
Wow. Oh, yeah.
Once a developer trains their brain to see that double equal sign as a literal question mark, their coding intuition just, levels up immediately.
Okay, so we've successfully asked our question with a double equal sign, and the computer has handed us back a true or false. But what do we actually do with that? I mean, how do we route the logic so the program takes action?
So we bring in the gatekeeper, the if statement. The if statement checks the condition, and it only runs the code beneath it if the condition is true.
And if it's false?
If the answer is false, Python just ignores that entire block of code, skips over it, and moves on to whatever is next in the script.
Okay, let me test this with a scenario. Let's say I am writing the logic for a school grading portal. I have my if statement. I write, if the student score is greater than or equal to 70, print you passed with a C.
Okay, good start.
But real life isn't just one binary choice. What if they got a 90? I need more options.
Right, so for multiple options, Python provides elif, which is short for else if, and else, which is your final fallback. Think of them as a team of security guards at a concert.
Security guards. I like that.
Yeah, so the if statement is the first guard checking the VIP list. If you aren't on it, you get passed to the second guard, the elif statement, checking the general admission list. You can have as many elif guards as you want.
And the else?
Finally, if you fail all those checks, you hit the else statement. That's the bouncer at the end who just says, you don't have a ticket, go home.
Okay, let's build that grading system then. Suppose my first line is, if the score is greater than or equal to 70, print you passed with a C. Then my second line, my second guard, is elif the score is greater than or equal to 90, print you got an A.
Right.
If a student logs in and they have a 95, wait, a 95 is technically greater than 70, does the computer print both grades?
Well, you've just built a wildly frustrating school portal.
Oh no.
Python is incredibly efficient, which means it reads from top to bottom and the very first true condition wins. Period.
So the student with the 95 hits that first line. Is 95 greater than or equal to 70? The computer says true. It prints, you got a C, and then what? Does it just stop reading the file?
It skips the rest of that specific conditional chain completely. Once the if or elif finds a true, it executes its block of code and immediately jumps to the very end of the entire security checkpoint.
It just bails out.
Yeah, it never even looks at your check for the A grade. The guard found a match, did their job, and clocked out. This is why the order of conditions is just as important as the conditions themselves. You always, always have to check for the most specific, highest requirement first and work your way down.
That top to bottom rule is a massive light bulb moment. But structurally, how does the computer actually know which instructions belong to which guard?
Yeah.
Other languages use those curly brackets to group things together.
Mm-hmm.
Python doesn't do that.
Right. Python relies entirely on blank space, indentation. It is completely non-negotiable.
Just empty space.
Just empty space. When a programmer writes, if age is greater than 18, the very next line must be indented, pushed to the right using the tab key or spaces. That empty space is what physically tells the computer this specific action lives inside the gate of the if statement.
And if I forget to indent?
If you don't indent it, the logic breaks. The interpreter will throw an error because it has no idea what you want it to do with the condition you just wrote.
So the blank space is literally part of the logic. Wow. Now, so far, we've been imagining perfectly clean numbers like a score of 95 just sitting in the code. But if you're listening to this, you know that whenever you build an app, you have to deal with users. Unpredictable, typo-prone human beings.
Oh, absolutely. The wild card.
Yeah. What happens when our pristine mathematical logic collides with a human typing on a keyboard?
It gets messy immediately, especially with text. Let's look at strings of text. Say you write a login condition checking if a username is Ahmad with a capital A. What happens if the human types Ahmad in all lowercase letters?
To me, that's the exact same name. I'd expect the program to let them in.
The computer absolutely will not let them in. Python is strictly case sensitive because of how it understands text under the hood.
How so?
Well, a CPU doesn't see the physical shape of a letter A, it sees a numerical code. In the standard ASCII encoding system that computers use, an uppercase A is represented by the number 65. A lowercase a is represented by the number 97.
Oh, wow. So when the computer compares Ahmad and Ahmad, it isn't looking at language at all. It's looking at a string of completely different underlying math.
No.
To the system, those two words are as radically different as, like, apple and banana.
Precisely. So to fix this, professional programmers sanitize the input. Before they ever allow the user's text to reach the if statement, they run it through built-in tools.
Like what?
They use a command called strip to magically erase any accidental spaces the user might have typed before or after the name, and lower, to force every single letter into lowercase. Then they compare that sanitized version against a lowercase master version in their code.
We standardize the messy human before asking the computer the true or false question. I love that. But here's another real-world trap I see beginners fall into. Imagine I build a web form asking for an age. I use Python's input command to ask the user, enter your age.
Oh yeah, classic scenario.
The user physically hits the 1 key and the 8 key on their keyboard. But when my code hits the line, if age is greater than 18, the entire application crashes wide. They typed a number.
The crash happens because of how computer memory allocation works. When a program uses the input function, it is designed to collect raw text, a string of characters.
But it's an 18.
Even if the user types the digits 1 and 8, Python doesn't load the mathematical concept of 18 into calculation memory. It stores a piece of text that just happens to look like an 18.
So it's basically taking a photograph of the number 18 rather than understanding the math behind it.
That is a perfect way to visualize it. A string is just shapes. You cannot do geometry on a photograph of a number. So when your code says, if this input is greater than 18, Python is looking at a photograph of text on one side and a pure binary mathematical integer on the other. It panics and crashes because it has no mechanism to compare text to math.
How do we save the program from crashing then? I mean, we need that number to do our age check.
We have to force a translation. We wrap the user's input in a function called int, which stands for integer. When you pass the text 18 through in, the computer actively converts those text characters into a mathematical number in the CPU's memory. Only then can you safely run your condition. Handling these data type mismatches is a huge, huge part of writing software that doesn't collapse the second real person touches it.
This brings us to a major escalation in complexity. Because if you think about any app you use, the decisions are rarely just one single question. The bank doesn't just ask, is your password correct? It asks, is your password correct? And D, is this device recognized? And D, is your account unlocked? How do we glue all these Booleans together?
We use logical operators, and, or, and not. These are the tools that let us combine multiple small conditions into one massive supercondition.
I know, make sure I have the logic right. If I use and, both sides of the equation must be true. If I say age is greater than 18 and he has a ticket equals true, they need both. If a 40-year-old shows up but forgot their ticket, the whole combined statement instantly collapses to false.
Yes, and is extremely strict. Every single part must be true, or, on the other hand, is forgiving. Only one side needs to be true to pass.
Give me an example of or.
Sure, if the condition is today Saturday or is today Sunday, the moment it confirms it's Saturday, the whole statement becomes true. It doesn't even bother checking Sunday. And finally, not just acts like a mirror, it reverses the Boolean. If a user is not banned, they are allowed in.
I want to throw a specific mistake at you. What happens if someone writes, if age is less than 10, age is greater than 30?
Oh, that's fun. You've created a logically impossible state. A number cannot simultaneously be less than 10 and greater than 30.
But does it crash?
The fascinating thing is, the Python interpreter won't crash when you write this. The syntax is perfectly legal. But the code inside that if state will literally never execute. It is a dead end, a phantom room in your program, entirely created by faulty human logic.
Okay, so chaining things together with and is powerful. But sometimes I see programmers use a different strategy. Instead of one long line of in statements, they put an if statement inside another if statement.
Nested conditions.
Yeah, I like to picture this as a courtyard of security gates. Gate 1, are you 18? If you pass, you step into the courtyard, but you aren't in the building yet. You walk up to gate 2. Do you have your ID? Why build this nested maze of gates when I could just use one and operator to check both at the exact same time? It seems like extra typing.
It is extra typing, but nested conditions give a developer a massive superpower: specificity and error handling. If you use a single and operator to check age and ID, and the whole thing evaluates to false, your program only knows one thing: the user failed. It prints access denied.
And the user's sitting there wondering, why was I denied? Was my password wrong? Is my account locked? Am I too young?
Exactly. The computer knows they failed, but it lost the context of why they failed. By nesting the conditions, putting gate 2 inside gate 1, you can attach a specific else fallback to every single gate.
Oh, I see.
If the user fails gate 1, the program catches it immediately and says, you are too young. If they pass gate 1 but fail gate 2, the inner else statement triggers and says, please upload your ID. That level of granular feedback is what separates a deeply frustrating user experience from a professional, helpful application.
We built these massive multi-gate security systems. But as a programmer, writing equals true, or checking if a variable is perfectly empty over and over again gets exhausting. Is there a lazier or more efficient way to do this as we get more advanced?
Python was designed to be elegant, and it handles this with a concept called Truthy and falsy values. In Python, you don't always have to explicitly ask a comparison question with a double equal sign. The language has a built-in intuition for emptiness.
What do you mean by an intuition for emptiness?
Certain values are inherently considered false in a conditional context without you having to ask. The number 0 is mathematically falsy. An empty string, meaning a user hit enter without typing any letters, is falsy. An empty list is falsy. The special null value, none, is falsy.
So if I'm checking if a user actually typed their username before hitting submit, instead of writing if username equals empty quotes, I can just write if username.
Yes. If the user hit enter without typing anything, the username variable holds an empty string. Python looks at that empty string, recognizes its inherent emptiness, and evaluates the condition as false.
That's so clean.
Right. If they typed Ahmad, the variable is filled with data, so it naturally evaluates as true. It's an incredibly clean way to check if data actually exists before your program tries to use it.
It feels much closer to how humans actually speak. And speaking of reading like human language, I want to talk about checking ranges. In a lot of older programming languages, You want to check if a user is in their 20s, you have to write if age is greater than or equal to 20 and age is less than 30. You'd have to write the word age twice. It feels really clunky.
Python lets you chain operators mathematically. You can simply write 20 less than or equal to age less than 30. It evaluates the entire range in one fluid motion. It reads exactly like a math textbook.
What about checking if something is part of a larger group? Like checking if a day of the week is a weekend. Usually I'd have to write if day equals Saturday or day equals Sunday.
You can bypass all those or statements using the in keyword. You construct a list containing Saturday and Sunday, and you just write if day in weekend list. Python will automatically search through the entire collection to see if the variable exists inside it.
That is so much better.
It saves massive amounts of typing and dramatically reduces the chance of making a typo in your logic.
Now, I have seen some code online where developers compress an entire if and else block into a single line of code, a ternary expression. Something like status equals adult if age is greater than or equal to 18 else minor. It looks incredibly slick. It looks like hacker code. Should we always be striving to use these one-line tricks to prove we know what we're doing?
The true mark of a professional developer is actually restraint. Yes, ternary expressions are fantastic for very simple assignments like the one you just mentioned, but clarity must always be the priority.
Restraint.
Yeah, if you take a complex, multi-layered decision about user permissions and cram it into a single massive line of code just to show off your skills, you are making it completely unreadable.
Because eventually someone has to come back and fix a bug in that code.
And that someone is usually you, 6 months later at 2 in the morning. When logic is broken out into clear if, elif, and else blocks with proper indentation, it is easy to read, debug, and understand. Writing clever code is fun. Writing clear code is professional.
Clear is better than clever. That is a great rule to live by. If you were listening to this, look at how far you've come. We started with the concept of a simple true or false Boolean test. We navigated the massive trap of assigning variables versus comparing them.
The double equal sign.
Yes, the double equals. We built wrapping logic with guards and fallbacks. We learned how to sanitize messy human text inputs, translate strings to raw math to prevent memory crashes, and we nested our logic to provide the user with clear, specific feedback.
It is a massive progression. But if there is one overarching mindset to take away, it is that conditions are not magic. When you are staring at a blank screen trying to design the logic for an application, don't think about the syntax first. Ask yourself 3 human questions.
What are they?
First, what exactly is the data I am testing? Second, what are all the possible outcomes? And third, which outcome is the most specific and therefore needs to be checked first? If you structure your thoughts that way, translating it into Python becomes the easy part.
Break the logic down into human steps before ever touching the keyboard. I want to leave you with a final, somewhat provocative thought to mull over. We've just spent this time learning how precise and rigid these true and false gates are. But think about the scale of this. Our entire digital world, every social media feed that decides which video goes viral, every banking algorithm that quietly approves or denies a mortgage, every artificial intelligence that filters job resumes. All of it is ultimately built on millions of these microscopic if, elif, and else statements.
It's all just gates.
Exactly. If the computer blindly follows the exact order of the conditions it is given, how many hidden human biases are permanently baked into the specific order in which those statements were written? Think about that the next time a platform mysteriously hides your post or an app denies a request without a clear reason. It wasn't magic. It wasn't a ghost in the machine. It was a programmer somewhere deciding which elif statement got placed first. You really don't want to be the robot blindly scraping against the wall. You want to be the one writing the conditions. Thanks for joining us on this deep dive. Keep asking those questions, and we'll catch you next time.